Question 3 is the first time on an exam that we've run into a series of questions where we have to predict the products from a series of reactions. Now, as we go forward in this course, as well as into Organic 2, this is something that we should expect we're going to see on every exam going forward. Some important reminders before we start looking at any of the specific questions. And that is to make sure we pay attention to what's most important in these problems. And that's looking for the functional groups that can react and knowing what the reagents do with different functional groups. So as this exam covered primarily alkenes and alkynes, that's what we should be paying most attention to in these types of questions. So part A here, we have just a single alkene to consider. And the reagents here tell us that this is a hydroboration reaction. Hydroboration, we should recall, is a reaction that gives us an alcohol, but specifically, because notice in this example, the two carbons of our alkene are not equivalent. And so the hydroboration reaction is what we call an anti-Markovnikov process. It gives us the hydrogen on the more substituted carbon, so the hydrogen we would add here, and it gives us the other group, which in this case is an alcohol, on the less substituted carbon. A Markovnikov process will give us the opposite. It will give us the OH or other relevant group on the more substituted carbon and the hydrogen on the less substituted carbon. And oxymercuration is an example of a Markovnikov process. And in part B, that's what we're looking at. So we have an oxymercuration type reaction, not dealing with an alkene here, but an alkyne. But the initial part of this reaction is what we would expect to see. We end up with the OH on the more substituted carbon and the hydrogen on the less substituted carbon. What's formed here, though, is an enol. And you should recall, as we've discussed in class previously, that in the presence of either acid or base, an enol will tautomerize to a more stable structure. And that more stable structure is the carbonyl. And so the final product here would be the ketone, where the OH initially went to the more substituted carbon and we got the tautomerization to the product. Part C, MCPBA, is an epoxidation. And so we just see that our alkene gets converted to the three-membered ring, the epoxide. Part D, we're looking at a hydrogenation reaction, the addition of hydrogen. Now recall that will add to an alkene. It will also add to an alkyne. What it will not add to is an aromatic ring. In fact, at this point in our course, we have not learned any reactions that will interact with aromatic rings. We'll save those for near the end of Organic 2. But what that means is these aromatic rings should always come through any of these alkene-alkyne reactions untouched. So there we can see is our aromatic unreacted, but our alkene gets reduced to an alkane, and our alkyne, which will first get reduced to an alkene, subsequently gets reduced to an alkane as well. Part E, we're looking at ozonolysis. And ozonolysis is a reaction that will completely cleave the carbon-carbon double bond. What we end up with is a carbonyl, whether an aldehyde or a ketone, on both carbons of what was the alkene. In many cases, that will give us two separate compounds as the product, but here, because the alkene is part of a ring, it will open up the ring, but it'll still be one product. Question F has a lot of different functional groups here. You can see we have these alkyl halides, we have an amine, we have an alcohol, thiol, phosphorus. But at this point, reactions like this, and we'll continue to see this with these reagents, hydrogenation is a reaction primarily of alkenes and alkynes. Given that we have no alkenes or alkynes in this starting material, nothing will happen here at all. Part G are the conditions for the Simmons-Smith reaction. The Simmons-Smith reaction, we know, is a method of converting an alkene to a cyclopropane ring. Part H, we have a halogenation reaction, which means we're adding one of each halogen to each of the carbons of the double bond. So each carbon of the double bond will get a chlorine. The other important piece of this reaction to remember is that the addition happens so that the halogens end up in a trans orientation. Lithium and ammonia is our dissolving metal reduction. It's one of the two ways that we have for converting an alkyne to an alkene and stopping at that point. The dissolving metal reduction is one that gives us the transalkene, and so that's what is reflected in our product, is conversion to the transalkene. And finally, the addition of HBr is a Markovnikov addition. It adds a halogen to the more substituted carbon and a hydrogen to the less substituted carbon, but the product that forms there is still an alkene, and we know that that can continue to react. So overall, we end up with two bromines on that more substituted carbon and two new hydrogens on the less substituted carbon.